All right, so let's get started. Welcome to your Monday. I like to kind of go over at the beginning of the week, go over what we're doing for the rest of the week. Get all this business out of the way. You'll see we are in the third week now of Thermochem. We are in where we are here, week 11. We do not have school tomorrow. It is election day. So we have a work day and you have a day off. So today we're going to talk about states of matter. This is not one of the hardest things, but I knew that this kind of like in between one day and then another break. I didn't want to give you the hardest stuff yet. But we're going to go through states of matter, just some stuff you have to know. Hopefully everybody's on the same page after today. And then on Wednesday, we're going to practice those Q calculations again, the Q to Q. If I know the Q of one thing, I can calculate the Q of the other, and then I can tell something about it. So if you were struggling last week with that when we did the bolt or the coffee pot or things like that, we're going to do that a lab again on Wednesday. And then hopefully by then you'll be able to do Q to Q and calculations on Q to Q calculations and interesting facts about phase changes for your quiz on Friday. The lab for Thursday, if I was being completely honest, I want to do a certain lab that we always do, but I don't know that we can do it with the COVID restrictions. So what I'm going to spend tomorrow doing is working out exactly what lab we're going to do for this Thursday for cohort A and for next Thursday for cohort B. So we'll do something on Thursday. I would like to burn food, but we will see how we're going to get that done. Then next week, the 9th, is going to be the hardest math of the unit. This stuff is tough. Calculating heat of phase changes. I'm actually going to give you maybe like a little mini quiz the next day. So I'll teach it to you the 9th, let you practice it on the 10th, maybe give you a 2 or 3 question mini quiz on it on the way out. Review on Wednesday. Cohort B will do whatever lab we just did. And then your test on this unit is on the 13th. So not this Friday, but next Friday. Okay. So kind of looking at where we are, kind of going along here. So hopefully everybody feels good. Let's get into the notes. So you do have a kind of guided notes, if you will, for this, because there is a graph and I didn't want you to have to draw it and all that kind of good stuff. So we do have this, but before we get started, I want to ask one question. So I have a beaker full of water here. If I take this thermometer out and turn it on, okay, I had preheated this, so it's kind of a little bit warm, but it is 65.9 degrees right now. I'm going to jot that down off to the side. It was 20.5 when I put it in there. 65.9 degrees, and we're talking Celsius. Okay. When I turn on this gas and I get out a lighter and I light this, and now it's on top of my Bunsen burner, what's going to happen to the temperature of that water? It's going to go up, right? Why is the temperature of the water going up? Okay, because there's fire. So is this an exothermic or an endothermic reaction down here? That's exothermic. So it's having energy go out. Energy is going into the water. We agree? What do you think that's doing to the speed of the molecules in there? They're speeding up. And when you speed up, the temperature goes up. Okay? So kind of just a little question. And you don't have to write any of this down, but just thinking. When you place a beaker of water over a lit Bunsen burner, okay, the molecules are gaining energy from the exothermic reaction of the Bunsen burner. That increases the movement. So your particles are going faster. Temperature is a measurement of average kinetic energy. So the temp increases. We get that, right? That's something you probably brought into this class today. Perfect. All right. Then I'm going to ask you a question. It's eventually going to boil, right? What's going to happen to the temperature of the water once it hits that boiling point? Any guesses? Is it going to keep getting hotter? Going to level off? Stops at the boiling point. What is the boiling point of water, by the way? Got it. Let's see if that happens, okay? So we're seeing what might happen when we boil. So we're going to let that roll while we're doing our notes. Like I said, the first part of the notes are really simple. So let's just get into it, shall we? We have to make sure that everybody's on the same page. Okay, everybody's taken, you might have taken physical science, you might have taken certain things in middle school. So I don't know where you're at. So we're going to get everybody on the same page today. We're talking about phases of matter. So we're not talking about types of matter. We're not talking homogeneous, heterogeneous, all that kind of good stuff. We're talking about phases. Okay, so we're talking solid, liquid, gas. There is a fourth state of matter called plasma. We don't really spend a lot of time on that. That's when you rip electrons off. That's what happens in your fluorescent lights and in the sun. Okay, so we don't take a lot of time on plasma right now. So let's talk about solids. In the first little box at the top of your paper here, if you were to draw a solid, how do you think you would draw it if you were drawing it at a molecular level? Where are you at? Here we go. You would probably just draw your dots right in order. They're kind of uniform. Remember, this is a very low entropy. Okay. Can the particles move in a solid? Yes, they vibrate in place. Are they moving past each other? No. Okay. Put your hand on your desk. Can you feel them vibrating in place? No. If you can, I suggest going to a doctor. But everything is made of moving particles. Okay. So everything's kind of vibrating in place. Perfect. Okay. A couple of fun facts that you probably know about solids, but just things that we want to make sure that everybody understands. Okay. And then so in the kind of little part next to the solids, whatever part of this you want to write down, again, these are your notes. In a solid, the particles are in fixed positions and they're close together and they vibrate. They're close together and they vibrate. Okay, you probably are aware of that. The other thing about a solid, though, is it's low on the kinetic energy scale. Low entropy, low kinetic energy. They also have fixed volumes and fixed shapes, if you care. Good, those are solids. After we have a solid, if we have more kinetic energy, we have a liquid. Oh, that guy wants to be a gas. Look at him evaporate away there. Okay. Okay. When you're in a liquid, the particles can go past each other. They're sliding around. They can eventually evaporate. All that kind of good stuff. In a liquid, the particles are close, but they can slide past one another. Particles are close, but they can slide past one another. Particles are close, but they can slide past one another. Awesome. You cannot compress a liquid. That's how we have hydraulic lifts and hydraulics on cars and things like that. You cannot compress. You cannot. And what that means is you can't change the volume. Okay, you cannot push those particles any closer together. Awesome. And that's more on the kinetic energy scale and also the entropy scale. So we're getting a little more disordered. We're getting a little more kinetic energy as we go along. All right. I'm going to take a moment here real fast. I see my water is boiling. So what I'm going to do, we are at 99.6. So I'm just going to write this off to the side and we're going to take a look at it in another second and see what happens. 99.6 degrees. Wonderful. We'll check it again in a minute. After liquids, you guys probably all know what's coming at you here. Then we have gases. Gases, the particles move independently of each other. They go exactly where they want, when they want, and they need a ton of energy to get to this point. Particles move independently and rapidly. Independently and rapidly. You can compress a gas, it expands to fill all available space. So in this room, there is not an inch of this room that does not have gas in it. As soon as you put gas in a balloon, it expands to fill the available space. You can also compress that. So the particles are far enough apart that you can expand and contract. You can compress a gas. You can change its volume. Okay. And they're very high on the kinetic energy and the entropy idea here. I'm going to check this again. Let's see what we got. Oh, 99.6. How fun. All right. We'll just keep checking. So again, those of you at home, the water is at 99.6 again. All right, so now let's do one other thing. And again, I don't think any of this is anything brand new for you, but you have now this little set of 3 beakers, and we're going to talk about phase changes. On that line, I'd write phase change is the conversion from one physical state to another. One physical state to another. So you go from a solid to a liquid, or you go from a liquid to a gas, or gas to a liquid, or liquid to a solid. I am not trying to insult your intelligence in any of these, but just making sure that we're all on the same page. So you have your 3 cups here. We are going to say that the first cup, when they're packed closely together and can vibrate in place, that represents a solid. Here they can move around. We're going to say that represents a liquid. And on the last cup, you have a gas. They're moving independently of each other with lots and lots of kinetic energy. Let's all just formally agree on what this is. When you have a solid, like an ice cube, and it turns into a liquid, what is that term called? Melting. Oh, I'm going to do the top one. Whoop. Melting. Go with the arrows, Mrs. Faye. Go with the arrows. Now, the next one, there are like 3 different terms I can think off the top of my head that people could use for the next one. If you have water and it turns into a gas, like it's doing right here, what are one of the things you could say is happening right here? Boiling. Okay. You also might say that it is the one that I'm going to use in this is called vaporizing. Vaporizing covers everything. Okay. Vaporizing covers both of these 2 down here if you want to kind of write off to the side. And we are going to write something down to the very important. So maybe write this off to the side. What's the difference between vaporizing, boiling, and evaporating? Let's talk. Boiling has to happen at a boiling point. Boiling for water has to happen at 100. Okay. Evaporation can happen whenever one particle on the surface gets enough energy, it can take off. Okay. So this happens on a particulate level. Boiling point is when it boils, so it has to hit a certain temperature. Vaporizing covers both of those. Vaporizing simply means liquid to a gas. Okay. All right, let's talk the way down then, shall we? Do you know what it's called when you go from a gas to a liquid? You find it on the side of your glass sometimes if you're at a hot day, cold glass. Yes, talk to me. You know it. Condensation or condense. And then liquid to a solid. If I take liquid water, put it into this large cold thing in your kitchen called a freezer, it will freeze. Okay. Awesome. There is one more that I like to make sure you guys know about because it is a little more common sometimes. If you go from a solid directly to a gas, you skip the liquid. We played with that on Friday, those of you at home, and last week when you guys were here. That is called sublimation. Sublimation is when you skip the liquid, you go solid directly to a gas. It's very, very hard to go gas to solid. It's called deposition if you care, but there's like no examples of that. But dry ice will actually sublimate. Okay, perfect. Now, one more big thing. Let's check this one more time so we can talk about it. Oh, my thermometer turned off. Oh, come on. I'm getting too hot. Oh, imagine that. 99.6. How fun. That was a good one. That's a good thermometer. All right, so we are at 99.6. Let's talk. During a phase change, we said it was 99.6, 99.6, 99.6. If I let this boil for another 3 minutes, what do you think the temperature is going to be? 99.6. So first of all, during a phase change, there is no change in temperature. I don't care if you're boiling, freezing, melting, sublimating, condensing. During a phase change, there is no change in temperature. Okay, what you would see on a graph is a flat line. And we're going to be talking about graphs here in a minute. What is happening? Why is this temperature not going up? It is clearly over a Bunsen burner. Clearly. And energy is clearly going in because it warmed it up. But what is that energy doing right now? That energy is not going to warm those particles. That energy is going to give every little particle of this liquid enough energy to be like, woo, I'm going to be at the gas. Wait, here I go. Okay, so as you give it more energy, it's no longer going faster. Okay, they're going as fast as they can in the liquid state. What that additional energy is doing is allowing them to break free from each other and turn into a gas. Okay, so you will always see a flat line on a graph when you have a phase change. Okay, speaking of that, we got a giant graph on the back. Let's label it up, and then I'll have you guys practice this business. Okay, so this will just keep going and going. 99.6. I guess we could have a sidebar. Why do you think this isn't at 100.0? Number one, this guy is probably a little off and uncalibrated. And there's a lot of airspace above here. If the metal measures all the temperature, this air is probably cooling down as soon as it comes out of there and leaves. Probably a little bit cooler air up here. Okay, but the main idea is that didn't keep going. It didn't go 101, 102, 103, 104, 105. It stopped exactly where it was, okay? Because that was undergoing a phase change. So what will happen, and again, you don't have to write this. You guys were right. The temperature stopped increasing. It was changing state. All the added energy basically just made it change state, okay? And you might have hit that at some point in time in your scientific career, depending on what you guys did earlier. All right, so we have the heating and cooling curve of water. Every substance has a heating and cooling curve. Basically, how hot you can make the solid, how hot you can make the liquid, and then you are moved into your gas. So there's a bunch of things we have to label. I know it looks confusing, so let's do it together. This is the heating and cooling curve of water. Okay, what are the most notable temperatures about water? Okay, well, first, if we are in this solid phase down here beneath this first kind of flat line, we know we are a solid. So let's go ahead and write down here, right underneath A, you have a solid. Okay, we are going to go up this scale first. This is temperature on the y-axis, and this is heat being added. So this is more heat, and this is less heat. Okay, it's ambiguous, just joules going in, okay? A solid, an ice cube, can get very, 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 very cold. If you go to our thermometer in our freezer right now, it's about negative 10 degrees Celsius. So keep that bad boy nice and cold. But that ice cube, if I brought it out here, can warm until what temperature does water freeze and melt on the Celsius scale? 0. So I know that we're going to write something in this little break here. So you kind of have to draw a little line. So that A happens at 0 degrees Celsius. Once the ice cube hits 0, boom. Now it will stop warming, and instead, remember, if you see a flat line, you know it's going through a phase change. And we just said on the other paper, once you go to a solid, you melt. So this flat line here, when we're adding energy, is melting, and then you turn into a liquid. Okay, does everybody see? So that flat line, an ice cube stays at 0 the entire time it's melting. Once it's completely melted, sure, then you can warm again. Liquid water can be between the range of 0 to how hot can liquid water get? We just did it. Liquid water can only get to 100 degrees. Once our liquid water hit 100 degrees, it had to stop and it had to boil. And I used boil this time because it is at 100 degrees, so it is at its boiling point. After it boils, it becomes a gas. Okay. Now, this is putting energy in, okay, in order to heat something, in order to melt something, in order to boil something. You have to add energy. So all of these processes are endothermic. You have to take energy in to speed up the particles or to get the particles away from each other. Endothermic. They take energy in. Okay. Awesome. Let's talk the reverse, shall we? If I were to then say that this is heat energy added going this way, if we were to talk this way, it would be removed. So now we're going to talk coming back down, and we're going to talk about removing energy. You can have a gas. Whoopsies heavens, that's silly. You can have a gas, and the gas can cool. The gas cools again till it reaches 100. Once it reaches 100, it can condense. It can condense. Once it's condensed, it's turned itself into a liquid. Again, liquid water is liquid between 100 and 0. But once it gets to 0, then it's going to stop changing temperature again, and it's going to stay at 0 the entire time it freezes. And then once it's frozen, it's going to be a solid, and that solid can continue to cool down. You know, if you had a piece of ice in the Arctic and it was negative 50 below Celsius, that's what the temperature ice would be. Okay. Now, last thing, these processes, cooling, you have to give off energy. Okay. In order to go from a liquid to a solid, you have to, okay, liquids have some energy. You got to give away energy in order to be stuck together and slowed down. So all of these processes give energy off or is taken out. Those are all exothermic processes. Okay. Awesome. So like I said, not the most challenging notes, but I don't know if you've seen a heating or a cooling curve before. Hopefully you're feeling good with all that. I made the lecture questions a little bit more challenging today to make sure, because I think everybody should know this by now. Hopefully you're having an easier time with that. So what I want to do is I do want you to do this worksheet because these are how the quiz is going to look like on Friday. And I'm not going to practice this again on Thursday. Thursday is going to be all about math. Okay. So you have a worksheet here. Looks a little bit like this bad boy. And I would also, because we still have like 15 minutes, so we got plenty of time, and I have a demo I want to do as well. What you guys are going to do is you're going to open up your Chromebooks. Even those of you at home, let's do this now. Open up your Chromebooks. You may use your notes. I would like for you to do the lecture questions. And then I would like for you to be able to do this worksheet. And the key should be in the Monday folder. We're week 11, friends. Can you believe it? Oh, heavens, get out of here. Oh, the key isn't in here. But I will put the key in here in a second, where I think maybe I had built in enough time for us to go over it. So there are the States that Matter notes, lecture questions. It looks more like the bigger quiz, but it's still only 6 points. I want to see if you guys really know this stuff. The assessment piece, let me put the graphs in, okay? So I'm going to put the music on quietly. I'm going to come around and see how you guys are doing out here. I'm going to see how you guys are doing at home. Again, I don't think this should be the hardest lecture. We needed a lecture to get everybody on the same page. We're going to rack up the math Wednesday, and then next Monday and Tuesday, get that math going. So you guys are finishing the worksheet and your lecture questions. Oh, lecture questions. You can just check the key. All right, you're going to stand right here. All right, what we're going to do today, you're right here. This is an extra special thermometer. Okay, go ahead and let that calibrate, see what the temperature of the air is. So, question. What could be worse? A boiling water burn or a steam burn? Right. Why steam? How hot can boiling water get? 100 degrees. How hot do you think steam can get? It can definitely go above that, right? So what we are going to try to do here, you and me, what's the temperature of the air over there?
26.3.
26.3. All right. So what we are at is the water in this container, we can guarantee you, is about 100 degrees, right? But once it leaves that, it can get hotter or it can get cooler depending on how things go. So what I want to show you right here is that I have water boiling, and then I have it going up through some coils. See these coils here? So the water, it's kind of like a tea kettle. It's going up through here, and then it's going through these coils. Now the coils are made of copper, so it's a really good conductor. So right now it's cooling it down. Can you hold the tip? Don't touch the metal part. Obviously that would be the wrong one. But if you want to come to this side, I don't want you to get burnt with steam. Kind of come to the edge here. Don't be shy. Right there. What is the temperature of that steam? It's hard to like hold it and read it. It's not very hot. It's okay. What are we looking at?
It said 62.
62 degrees. That's because as the steam is
67.
67. As the steam is going up, it's cooling down. Now, if I reverse that though, and now I'm going to start to heat up these. If my propane will stay on propane. There we go. What I'm going to do is I'm going to start to superheat this steam. This is called the superheated steam demo. I'm going to get really mad at this guy. One more time, and I'm going to replace you with a Bunsen burner. Okay, and now what I'm going to do is I'm going to start to heat this steam. Is our steam going up in temperature? Well, it would if it had consistent heat. What's happening to the temperature of our steam?
Kind of inconsistent.
Yeah, I think probably because I'm being inconsistent over here on the heating side. Heavens to Betsy Lou.
That's at 70.
70 degrees. All right, we'll get that going. Remember, anything over 100 is over the boiling point of water. Now, what do we got?
Gotta hold it better.
Yeah, go ahead. Get comfy. It's nice and warm up here. How hot are we thinking now?
Very. It keeps changing.
Is it going up or down?
Both.
Cool. Good night. Good, yeah.
That's going down.
No, we're going to get it right here. There we go. All right, now what's the temperature of that steam?
58, 58. 84,
84,
105,
105,
113,
119,
140,
140,
155,
155. All right, thank you. I got you. Now, this steam, you're good. You can put that down. This steam can actually get really, really, really hot. I appreciate it. You're good. You can actually just drop your goggles right there on the edge. This steam can get so hot that I can actually light a Bunsen burner. So you got about, what was the highest we saw there? We saw 155. If I work on this and I can get this steam to be up near 155 again, what you can do is you can use this steam here to light that match, to light a match, okay? So all I did was have that steam. We'll do it again. Don't set my desk on fire. I'm getting that temperature to go way, 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 way above 100 degrees, and that steam will light that match, okay? Oh, all right. So again, that steam went way above 100 degrees because it can, because now it's in a phase. Lighting matches with steam. Thank you, guys.